and gentlemen, welcome to the Advanced Materials Forum for Europe. I'm delighted that you can join us in this online event. Because of the coronavirus situation and to keep people safe, we are doing this online from our home offices, and I'm in the Netherlands in my home office. By way of introduction, my name is Raj Mathur, and I am the Global Manager for our Advanced Thermoplastic Composites program, or what we refer to as ATC in short. My background, work, and education is in metallurgy, in ceramics, and in composites. I started in thermoset composites in the aerospace industry, and then more recently worked on long fiber thermoplastic injection molding compounds. And currently I'm involved in continuous fiber reinforced thermoplastic composites for the automotive industry at DSM. So the topic of today is indeed continuous fiber reinforced thermoplastic composites, which, as you can tell, is a mouthful. We simply refer to this as advanced composites, and also by their form factor, which is UD tape or unidirectional tape. I'd like to start with the what and why of these materials. Why are they of interest? What exactly are these materials? And then I'll have a few comments on the form in which they are presented to the industry for composite processing. And then I want to talk about manufacturing with these materials in the second half of my presentation, which is very important to understand. And then share with you what the customer feedback has been so far and how DSM has put together a strategy which is in tune with our customer needs. I'd like to conclude with a note on sustainability, which is a very important issue at DSM, and talk a little bit about how we are contributing to this important category for better outcomes. So what are these advanced composites? Well, as I mentioned, these are continuous fibers, sometimes also referred to as endless fibers, that are held together with a thermoplastic polymer. These fibers are called also unidirectional tapes because they are oriented in one direction, which is the direction of the length. So that is why they're referred to as UD tapes as well. And the other aspect of these UD composites is that when you make parts from this, fibers, the parts are reinforced with fibers from one end to the opposite end in all directions. And what that means is that when you pull at this part, when you twist it, when you bend it, what you're really bending and twisting and pulling at are the fibers. And it is the fibers that form the skeletal network or backbone of these materials, and that's where the high mechanical properties such as stiffness and strength come from. So if you look at the property profiles of these materials and compare them to injection molding materials, you'll see that if you take the nominal value of tensile strength for injection molding materials, they're approximately between 200 and 300 megapascals. But with these UD tapes or advanced composites, you can go up to as much as 2100 megapascals. Similarly, when it comes to the stiffness or modulus of these materials, the nominal value for injection molding compounds, which are discontinuous fibers, the nominal values are somewhere between 25 to 30 gigapascals, whereas over here, you can go up to as high as 125 gigapascals. So the chart to the right-hand side basically positions these materials, metals, advanced composites or UD tapes, and the short fiber thermoplastic injection molding compounds so that you can get a rough idea, an overall idea about what the perform is and what the cost might be. Now, how does it compare to metals? I'd like you to take a look at this slide. It's a fairly busy slide, but we'll start from the very left. These are essentially 2D plots of tensile strength on the y-axis and tensile modulus on the x-axis. The data points indicated in yellow circles, yellow ellipses refer to UD tapes and composites made from them. The blue circles or blue ellipses with the data points refer to metal. As you can see in the left, the properties of UD tape-based composites is much higher than aluminum or magnesium in strength and in stiffness. Compared to steel, these materials are higher in strength, but somewhat lower in stiffness. Now, on the right-hand side, we have the same plot, except that these strength and stiffness values have been normalized to the density of the material. In other words, when you compare a 1 pound weight of metal to a 1 pound weight of composites, you now see that the material properties of UD tape-based composites are much, much higher when normalized to their weights. And this is the reason why the industry is interested in these materials, which is that they offer mechanical properties comparable to metal, but with much, much lower weight. Coming to the automotive industry, here is a survey done of available technologies in the industry and their impact on reduction of emissions measured in grams of CO2 per kilometer driven. So to the left, you see a list of all the technologies such as start-stop at traffic lights, or making the cars more aerodynamic, or reducing the rolling friction resistance to the road. All of this help in lowering emissions per kilometer driven. But as you see at the very bottom, it's the extreme lightweighting, and they refer to as at extreme when you're using UD tapes, that you get the biggest bang for the buck when it comes to reduction of emissions. And this is the reason why the automotive industry has shown a great interest in adopting these materials and substituting metal with composites. This shouldn't come as a surprise to us because 25% of fuel consumption in a passenger car is strictly to counter the weight of the car, the inertial mass of the car. But we can also look at it from an emissions point of view. And so here is a chart on the emissions at different stages of the life cycle of a car. An average life of a car would be anywhere between 8 to 12 years, I think. But when you look at the emissions, you see that it's not so much during the raw materials usage or the manufacturing of the car, but it's actually the actual running of the car that emissions are the highest. Therefore, it behooves us and the industry to reduce the weight of the car for the 6 or 8 years that it's driving so that the CO2 emissions are also lowered. Now, the form factor, and what we mean by the form factor is how do you present these UD tapes to the industry? The one that we have settled on, of course, is tapes. We are talking about continuous fibers, long ribbons of them held in place by thermoplastic polymer. So the natural form factor for this is long strips of tapes used for manufacturing. Now, with these tapes, as shown on the rolls over there, you can also weave them into mats, like a plain basket weave, and create mats or sheets. And these sheets can be piled up on top of each other to make a thicker laminate or thicker sheet. Finally, you can also take the UD tapes and just place them one above the other in a process or description that's called cross-ply, but you can vary the fiber angles. And again, the idea is to make sheets of composite materials based on UD tapes. But there is also another way of presenting continuous fiber composites, and that is you can take these continuous fibers and weave them into fabrics, much like making clothes. And in Europe, they are referred to as organo sheets historically, but in other markets, the more conventional reference is 2D preforms. However, we do not make these 2D preforms for very clear reasons. As shown on this slide, when you want to make a specific shape, you have to cut out a lot of material from organo sheets, which leads to a lot of scrap waste. Whereas with the UD tape, you place the tape where it is needed, and therefore your scrap rate is 5% or less. So that's one good reason for thinking of UD tapes as fundamental building blocks. The other one is that in the fabrics, the fiber orientation is fixed. Fibers run in the length direction and in the width direction, or 0 and 90 as we say. But with UD tapes, you're free to orient the fiber as needed in the direction of where the stresses are, not just randomly 0 and 90. The other aspect, of course, is that the organosheets or 2D freeforms have lower properties. And why is this? Because these fibers are woven together. And every time they come together in a weave, you are essentially kinking the fibers or crimping it, as the industry calls it, which means it leads to a loss in mechanical properties and also a potential site for failure. Whereas with UD tapes, you don't see that. And this is very clear when you look at cross sections of composites made from organosheets or UD tapes. And finally, UD tapes can be used to build thicknesses where needed. Parts are rarely of a single uniform sectional thickness. So with organosheets or 2D freeforms, you have only one thickness. Whereas with UD tapes, depending upon where you need to add thickness, you can do that very freely. So these are the advantages of using UD tape over organosheet. But this is not to say that organosheets don't have a use. For example, when you're covering large surfaces like an aircraft wing, it might be speedier to use organosheets to cover that surface by just unrolling the fabric, provided you can also meet the mechanical specifications. A portfolio of DSM tapes on this slide. We show the various polymers we have in our portfolio based on polyamides. This is PA6, 66, 410, and PPA, and also PPS, or polyphenylene sulfide. On the y-axis, you see the melting temperature, and on the x-axis, you see the glass transition temperatures. This is so that you select the proper polymer depending upon the temperature of the application. To the right-hand side is a table giving the physical characteristics of these tapes, 0.25 millimeters in thickness. The length can be anything, but normally we stop at 600 meters because the roll gets pretty big, 60 centimeters in diameter, and gets pretty heavy, 150 kilograms. So most customers are satisfied with that, but there's no reason to not make them in kilometers long, for example. What we like to tell our customers is rather than having a standard stock keeping UD tape, mother roll or master roll, we like to make tapes which are specific to your needs. So if you tell us that you want a particular thickness of maybe 0.1 millimeter, we can do that for you. If you say that you don't need 50 weight% of fiber in it, we can lower it or increase it to your needs. So in other words, the way to optimize cost and stock keeping units is to make it fit for purpose. Now, obviously, we have to give a lot of supporting information, and data sheets are very, very important over here. This is so that part designers have the properties to model their use in their specific applications. Now, one of the things that DSM is doing very well under the auspices of the AVK Society in Germany is that a lot of suppliers and users and other actors in the value chain have come together to create what we hope will be the ISO standards for how these materials are tested and how the data is reported. Furthermore, we hope this information is already in public data sheets or data sites such as Campus, but we are more than willing to provide this information to our customers personally as well. Secondly, in addition to the basic mechanical data, we also have material cards so that these materials can be modeled, for instance, in high strain rate applications such as impact or crash worthiness of a car. We have all the material cards that you might use in software such as LS-DYNA. I must also add that customers have requests for mechanical properties at different temperatures, in different environments, where the relative humidity is not just what is considered normal, but can be high, such as 80 degrees. So we have a lot of this information with us. And because the mechanical properties are specific to the fiber orientation, we also provide you information of mechanical properties at angles to the fiber orientation. So if the fiber orientation is considered as 0 degrees, we can give you mechanical properties at right angles to it or at any other angle to it. Because these are not isotropic materials like metal, handling the information and designing with UD composites does require some deeper thinking. And this is where we work with our customers, because we have a very vibrant, very rich CAE department, computer aided engineering department, so we can help you in all your simulation studies, and we take an integrated approach. So as seen on the slide, we are looking at a bracket that was formed from a laminate made from UD tapes, thermoformed to shape, and then overmolded with injection molding compounds. So the integrated approach that we use over here is, of course, we do the flow simulation to understand and optimize the molding process, but we also look at what the resulting fiber orientation will be, what the warpage might be due to overmolding, and also the adhesion between the overmolding and the underlying UD tape composite. Then we look at the mechanical simulation. In this example, this bracket is being simulated for a load acting on it, and the goal is to understand what kind of deformation you get. So we use the microstructural information that we have for these kind of composites to predict the macro properties. So the next slide will show some data fitting that we did based on simulated and actual testing, and you'll see that there's a very close fit between the curves. Those curves are independently for various fiber orientations. And so it is in 0 degrees, which means in the fiber orientation, or at 45 and 90. That's what those various curves are about. But there's a good fit between what is simulated and what is actually tested. In other words, one way of summarizing our CAE approach is that we look at microstructural details to predict the macro properties. Now, moving into the second half of my presentation, how do you manufacture with UD tapes? Over here, I have listed the most common methods of manufacturing with UD tapes. Number one, of course, is, as I mentioned earlier, UD tapes are made into laminates. Think of the equivalent as metal sheets. They are thermoformed to a shape, and that would be the equivalent of metal stamping. And then they are overmolded with injection molding to add features such as ribs and pin bosses and fastener sleeves, etc. The other use of UD tapes that is quite common is that they are used for local reinforcements of injection molding materials. So an injection molded part is doing just well, but needs a certain amount of reinforcement in a certain specific area. In this case, you take the UD tape and you insert it in the tool, and then you overmold it so that you get selective or strategic reinforcement where necessary, thus making an injection molded part a much bigger part because of the enhanced properties. And finally, as you can imagine, UD tapes are also used to wind pipes, cylinders. One example shown over here, of course, is pressure vessels that's used for the storage of CNG or hydrogen gas for fuel cell batteries. This is something that we do very often with our customers as well. So these are the three basic ways in which UD tapes are used to manufacture real parts. Now, keep in mind that UD tapes cannot make very complicated shapes, and that is where injection molding comes in, which adds features such as ribs and other parts. Some examples, and over here I ask you to understand that we cannot share our current customers' programs because of confidentiality agreements, but you see some common parts that are made by UD tapes. So to the left is a front bumper beam. Believe it or not, it starts as a flat UD tape laminate, which is thermoformed and then overmolded with ribs. In the middle, you see what could be an engine cover or a battery tray or a trunk recess. And what you see over here is again lamination, thermoforming, and overmolding. To the right-hand side, you see some pipes that have been made by winding UD tapes, and these are used to replace steel beams in automotive construction. So, for example, they can be used in a crosscar beam. And below, of course, you see the bracket that I had mentioned in my previous slides. Some other applications which are in the public domain. To the left, you see a composite door panel. This was made by taking UD tape and weaving it into a laminate and then thermoforming it to the shape. This was done with Jaguar Land Rover, and the weight saving was about 70%. And furthermore, it was tested with a side pole impact, and therefore it was considered crash-worthy. In the middle is a steel wheel rim. These wheel rims are typically 2 millimeters in thickness, sectional thickness. So we removed 1 millimeter of metal, and then we wrapped UD tape on strategic areas of the steel wheel. And we had 2 kilograms weight saving per wheel in a passenger car and 6 kilograms per wheel weight saving in trucks. Furthermore, they were subject to rolling fatigue, which is the most critical test for wheels. And not only did we pass the test, but we increased the fatigue life by 30%. And when we looked at the failure, it was not in the composite, not in the interface between the metal and the tape, but in the underlying metal which had cracked. So all of these experiences have taught us a lot about how to bring dissimilar materials and create adhesions at the interface. Finally, to the right-hand side is a floor module, almost 2 meters long and about 1.5 meters wide. This was done with Fiat, and again, it was a process of lamination and thermoforming to final shape. So these examples illustrate the manufacturing methods that I've talked about. But now coming to the market and the customers, what have we seen? Well, let me begin by saying that what you see on this slide is the value chain, starting with raw materials, which is fiber and resin. You make UD tapes, and then the UD tapes are laid up to make laminates, consolidated, and thermoformed to the shape that the buyer wants. But what we have seen in the industry is that the buyer has no idea about how to go from the starting materials to the final part that they desire. And this is for historical reasons. The composites industry has always been fragmented. The technologies exist, but they have not come together into a supply chain that is transparent to the automotive industry. So what we have done in our approach is create technology partnerships in that supply chain so that this information can be given as a package to the end users. So what do? Knowing that this is the automotive industry, we make sure that the cost of making UD tapes is not very different from that of processing other materials. Secondly, we know that cycle times are of great importance, so we keep cycle times down to about 1 minute or 2 in any manufacturing method that we choose. And finally, there is no extensive retooling required. The press used to make sheet metal parts can also be used for composites. But the key thing over here, of course, is creating partnerships in this value chain so that we can bring the solution to the customer, which I think is a win-win-win situation. I'd like to end this presentation with an emphasis on sustainability. This is something that DSM deeply believes in. Some of the polymers that we use are bio-based from the non-food chain, and they have a zero footprint. Furthermore, we will have recycled content in our polymers in the coming years for all the UD tapes that we make, up to 30%. So here is an example of where we have demonstrated circularity. We have taken some of our discarded parts, and these are pressure vessels that were used for storing gas. The metal fittings have been removed. They were ball milled to a specific size, 3 millimeters. And then these were injection molded. And this slide shows you the comparison between the reground or regrind material and the original virgin material. And what you see is that there is at least an 80% retention of the properties as shown in this table and the curves to the right-hand side. So what that means is that we can set up a cradle-to-cradle application with most of the advanced composites that we are using. In conclusion, what I'd like to say is that you cannot make everything with UD tapes. You have to use a combination of materials to reach the goal, because the focus is on lightweighting and not on composites per se. So as I've shown you, we use combinations of UD tape, advanced composites, but with injection molding. We are very free to use metal inserts if necessary, use metal fasteners. All of this is okay with us, because the metric that decides whether this material is of value is not so much the material per se, but the cost per kilogram of weight savings that you achieve, any additional cost. Hopefully there is no additional cost, but if there is an additional cost, the buyer needs to understand what is the cost, extra cost that he pays, the differential price for every kilogram of weight saving. So in conclusion, we are leveraging UD tapes. We think of UD tapes as a fundamental composite building block, and we insist that the entire supply chain or value chain be transparent to the customer. We also take care that we have technology partnerships so that we can go with a complete solution to the customer, which is a win-win for everybody involved. Our conversion costs are low, and we take care that the equipment used to make these parts is not something very exotic, like, for example, autoclaves that are used in thermoset composites, but more like lathe machines and presses, which is something that the industry is very familiar with. With that, I'll end my presentation. I invite questions from you. Please use the chat function to post your questions, comments, and I'll be very happy to get back to you personally. And secondly, I invite you to join us, team with us to come up with some lightweight solutions for the automotive industry. Thank you very much.